Gottfried Wegener was born in 1880 in Germany. He was one of those rare people that's just good at and interested in a lot of different things. He got his degree in astronomy, but went into the relatively young field of meteorology, where he pioneered the use of balloons to track air currents and went on expeditions to Greenland to study polar weather, at which he was totally badass. He spent winters in a hut drilling ice cores, and he also made the longest crossing of Greenland's ice cap on foot, for the win. But he was also interested in other stuff, including geophysics, which is why he got totally obsessed with this. He couldn't help but notice, like some school children will, that Africa and South America almost look like puzzle pieces. Sure, they're thousands of miles apart, but they really look like they fit together. Of course, other people picked up on this. Like I said, you probably did around 4th grade. But another one of Wegener's great qualities is that he wasn't afraid to ask the stupid-sounding questions. So he just started asking people, continents moving, is that a thing? And if it was a thing, how would we know that it was a thing? And because he was a voraciously curious guy, he was looking for the answers to those questions in all kinds of places, and guess what? He found out that fossils of the same plant species had been found on both sides of the Atlantic. He discovered that the geology of the Appalachians was almost identical to that of the Scottish Highlands, and he learned that distinctive rock strata found in South Africa were the same as in parts of Brazil. Almost as if the continents, I don't know, drifted. Finally, in 1914, while laid up in a military hospital bed during World War I, he pieced together his theory that all of the land masses on Earth used to be part of a single continent called the Ur-continent.
Land features such as mountain formations and events such as earthquakes happen due to the continuous movement of the tectonic plates. As these plates keep moving around the Earth's surface, they shape our world. As the tectonic plates move, they collide with each other. The plates can collide in many ways. Sometimes, when two tectonic plates move towards each other, one of them is forced downwards. This is called subduction. Yet sometimes when they push against each other, they are both crumpled. This is called uplift. You'll be surprised to learn that this is how the Himalayas were formed. At times, the tectonic plates collide sideways. This is called the transform movement.
Margins, lithospheric plates move in opposite directions. The plates, which include crust and part of the upper mantle, ride over the asthenosphere.
Now, a convergent boundary is where two plates meet and push against each other. Now, there are 3 ways this can happen. The first is if you have an oceanic plate, usually that's underwater, pushing against a continental plate. That's one of its continents where land is. When those push together, what almost always happens is the oceanic plate will subduct under the continental plate. Subduction is a process where one plate will go under the other. It'll usually get pushed back down into the mantle and be melted back into magma. The landforms that are created here, often you'll have a lot of mountains forming on the continental plate as it gets pushed up by the oceanic plate. You'll also have a lot of volcanic activity happening on the continental plate right here. The second type of convergent boundary is when a continental plate pushes against another continental plate. Now, unlike the other 2 types, this actually does not cause subduction because these are generally the same density. They will push against each other, and they just kind of smash together, and usually what happens is some uplift. So they'll smash up, and you'll see some mountains created right here from the 2 of them being pushed together. It's another place you'll see a lot of volcanic activity. The third type of convergent boundary is where an oceanic plate and an oceanic plate will mix. We have this drawn down here. This is the ocean, water on top, and the 2 plates, the land underneath the ocean, pushes together.
Mantle is cooler and more rigid than the deep mantle, and in many ways acts like the overlying crust. This rigid unit of rock is identified as the lithosphere. The lithosphere tends to be thinnest under the oceans and in volcanically active continental areas, such as the western United States. The average thickness of the lithosphere is measured approximately 50 miles or 80 kilometers.